I learned about some engineering ways that maybe can vastly speed up fusion. And that's where I got the bug. It said like, whoa, not only can we do space propulsion, that's great with this physics and engineering, but maybe we actually have a chance to do fusion on timescales that are relevant for humanity, relevant for me personally.
Hi, everyone. Welcome to Behind the Tech. I'm your host, Kevin Scott, Chief Technology Officer for Microsoft. In this podcast, we're going to get behind the tech. We'll talk with some of the people who have made our modern tech world possible and understand what motivated them to create what they did. So join me to maybe learn a little bit about the history of computing and get a few behind-the-scenes insights into what's happening today. Stick around.
Hello and welcome to Behind the Tech. I'm co-host Christina Warren, Senior Developer Advocate at GitHub.
And I'm Kevin Scott.
And today we are bringing you a conversation with someone who is at the forefront of the future of energy, David Kirtley, who is a co-founder and CEO at Helion.
Yeah, I've gotten to know David over the past few years, first because, just out of general interest for cool things like fusion generators. I got an opportunity to tour their facility and to see the machine that they were building. And then Microsoft has been partnering with Helion to try to figure out how we can be the first consumer of the energy that their first reactor produces, which is enormously useful to us. Obviously, we use energy in our data centers, and we need that energy to be clean and sustainable and as cheap as possible in order for us to deliver all the cloud computing to all of the customers who need it.
No, definitely. And I'm super excited that, we're working with companies like this, and also, frankly, that there are still companies that are doing this sort of research, because when we talk about the future of energy, I think that fusion sometimes gets the short end of the stick. And I personally think that it's a really important area for us to be building towards. And so I think that I'm glad that people like David are out there and that we're working towards this.
Yeah, and I think it's not just getting sustainable energy, which is super important, obviously, but the idea that we may be inventing a technology right now and like close to actually having fusion after doing so much research and so much engineering over many, many, many decades, really opens up the possibility that we may be able to have more energy abundance than we have had in many decades, which I think helps us solve so many problems that we have and is going to be surprising in ways that people don't even anticipate fully, like once we have it.
Yeah, definitely. Well, let's go ahead and get into this conversation with David.
Dr. David Kirtley is a co-founder and CEO at Helion, a privately funded nuclear fusion company. David's passionate about inventing and developing disruptive technologies that will improve access to energy, reduce carbon emissions, and provide a better future. He's a fellow of the National Science Foundation, NASA, and the Department of Defense. Now, he's a leading expert in field reverse configuration fusion generators and leads a team working to build the world's first fusion power plant. Just this year, we announced that Helion is going to provide Microsoft fusion power starting in 2028. David, welcome to the podcast. Thank you so much for joining me today.
Thank you very much. It's great to be here.
So I start each one of these conversations by asking my guest how it is they got interested in science and technology in the first place. And so I'd just be curious, like when you first got the spark and what that looked like, what encouraged it, and just, how you got on this journey.
Yeah, that's wonderful. So I actually look back and can point to a couple of parts in my history. I grew up in the military and in the Navy. Actually, my father was in the Navy. Every 3 years, we moved somewhere new. And one of the places that we lived was Bermuda, Naval Air Station Bermuda. Kind of a great place to be a 10 and 11-year-old. But it was under the flight path of the space shuttle that would launch out of Florida. And
wow.
At night, you could see, when they did night launches, this man-made comet flying through above you and just lighting up the sky and looking like, hey, we humans built this thing. There are people up there and they're going into space. Like, technology can do this thing. I want to follow this, but I don't know how to apply it yet. Interestingly, the next sort of big spark came in high school, where I was in physics, physics in high school, AP physics, and my physics teacher was a particle physicist who had been working for many years in Texas on the super collider there. And this is when I learned math and physics for real, and calculus and all those core things that define your ability to solve these problems. And it was always applied. It wasn't let's learn force and acceleration. It's let's understand how roller coasters work. It's let's not learn thermodynamics. It's let's understand how fire works and chemistry through fire and those kinds of things. And started to see like the universe is based off of math and physics, and it's digestible. You can understand it, you can learn the rules, and then it makes sense. And you can apply those to do new things. So the two of those, both the scale of what humans are capable of and then the understanding of the mathematics behind it all, really got me very excited about this. And then that also got me into energy and understanding the energy problem and how it applies to humanity and how maybe we can work to make that better.
Super cool. Well, so I want to talk about your teacher for a minute. Like, do you know how a particle physicist wound up teaching high school?
Yep. So this is also an interesting lesson in that it ties back to some of the things we do as a private company in a space dominated by large academic and national lab infrastructure projects, is that there was a large effort for a while in Texas to build the world's largest super collider, a particle accelerator, the superconducting super collider. That was going to be this massive thing in North Texas. It was going to be a very large project to do really amazing physics. And it sort of got so big, my understanding now, I didn't really understand at the time, it got so big and took so many years that it's sort of like crumbled under the political weight of trying to deploy massive amounts of capital for this huge project. And then other things like land rights and regulatory requirements and other things probably added to that. But even now, I don't really see the whole picture there. And so he, as far as I'm aware, moved to Texas to be able to support this and work on that project. And then while it was taking the years, started teaching physics at high school and then fell in love with that also. And
That's unbelievably amazing, actually. Like, I wish more kids had that option, because I do think, I'd be curious in your take on this. One of the things I see with my own children, and like I saw it with myself, although I didn't recognize it when it was happening, is like sometimes you get into these like really great feedback loops personally, where you find a thing that's interesting and you're kind of good at it. Maybe you're not the best at it, but like you're good enough and you're excited enough about it where you learn more, you do more. And by doing, you get better at the thing. And the better you get, like the easier it is. And like the more excited you get, the more, accomplishment you feel. And like the sooner you get those cycles going, and like the more you can turn the crank, I think the more you can ultimately achieve. And so it's really fantastic when kids get the cycle started. Like, I don't know whether you've experienced that yourself or you've seen it in other people, but like I just, the phenomenon, even with like, prodigies at things like piano, like sometimes I think it's about talent, and sometimes it's about like, you just have the right set of conditions to start the feedback cycle where you get like all of you get very quickly up to this level of competence because you're just practicing so much.
Yeah, I think that I look back at my history and I have the visual of, like a flower unfolding. As you open it up, there's more and more things as the petals open that you get in. It's more complex. It's more interesting. And so in this case, for instance, like there's a specific memory here where we were learning F equals ma, force, mass, and acceleration, right? But they're all abstract thought process of what is acceleration and what is gravity and what is gravitational potential energy and all of those things. And so you start to look at the application. Okay, roller coasters are a good one where there's acceleration and gravity and energy and conversion of kinetic to gravitational potentials. Like all of that is wonderful. But you say, well, great. Well, how am I going to measure that? And so you learn about accelerometers. And then you learn you need to program those accelerometers. And then you learn about data acquisition. but it has to be handheld so you can get on the roller coaster and you actually do it. And then afterwards you analyze the data and you learn about signal to noise in the data. And all of those things just like keep compounding and getting more interesting and make you want to spend more time doing it. And then you have to learn the mathematics behind why all that works. And then you start to learn, okay, well, what is gravity? And then it just unfolds this physical understanding of like the universe, but you also get passionate and excited about it. I think about that with my own child, of looking for the things that are sparking him without trying to like push him into a specific category.
Correct.
Because it has to be downhill. It has to, as you kind of said, snowball, and the energy has to go into the passion of understanding and growing, and getting better and better at it, rather than someone pushing you into it.
Yeah, I had this moment with my daughter this week, my 15-year-old, where she is just obsessed with chemistry and biology and medicine. And she just had this moment, like literally last night, she was sitting down doing some science homework, and she was excited about it in exactly the way I remember at 15 years old being excited about programming computers and computer science. And and I told her, I was like, I think it's wonderful, kid, that like you found this thing at 15, because I realized in retrospect how lucky I was to have found my thing when I was 12. And it wasn't about me being talented. It was like about me, again, getting into that positive feedback loop pretty early, almost by good fortune. So I had this other thing I wanted to ask you. I still haven't seen the Chris Nolan Oppenheimer movie, but I did go watch the Oppenheimer documentary about his life. And one of the interesting things in that documentary is that he started off his PhD program at Cambridge trying to be a lab physicist. And was just evidently miserable at it, like hated it, like wasn't very, very good. And he wound up going off to Göttingen to be a theoretical physicist, and so like he found the right mentor and like found the right space. And like there is this cliquishness, I find, like it's definitely in computer science. I think it's in physics and the physical sciences as well, where there's this real divide between theoreticians and like folks who do applied work. And like I've always been more on the applied side myself. Like I get motivated to learn the theory by finding a problem hard enough that demands that you understand the theory to go solve the problem. But like the thing that really excites me is like, here's a gnarly problem we've got to go solve. And other people are like really motivated by like living in the abstract, like I think Feynman was one of those guys where, like he just like had this, intellectual life where he could imagine worlds in his head and like get really excited about that. And, not to say he didn't go solve real problems as well, but like, do you think that exists? Have you experienced that as a physicist in your own career?
Yeah, I think that I think about it as we actually ask this as an interview question, typically. And we ask it in a number of ways, but there's a Venn diagram of how much do you gravitate towards theory, experimental or hardware, and computation. And we actually put them in 3 individual buckets of different versions of applied and different benefits. And typically at Helion, we hire people that can do a little of all of them. Like that's a pretty hard requirement, that you can do some. And then we ask essentially like, tell me about where you've been in your career. Have you been focused on hardware or theory or computation? But now where do you want to go? What drives you? What's your passion? What do you wake up in the morning thinking like, oh, I want to go build this thing, or I want to learn more on the theory of the things I've been building for my PhD work or whatever. And so yeah, I definitely see that, and different people gravitate towards different things. And to build real systems, you need all of it, right? You need some.
Correct.
You have to have theory, otherwise you're not going to build a thing that works. You have to have simulation, so you don't have to just trial and error everything or use empirical studies for everything. And so you have that mix. And so I think that's true. In fact, in my background, we haven't talked about this too much, and we can. But when I got into Fusion, I got into it as that applied, the desire to build and test these things. And I struggled early, actually, because it was so theory and so far out in timeline and in application. And I had to actually take a pause in my career in Fusion and look at it and decide, what do really I want to focus on?
Yeah, and it's so interesting. Sometimes people, I think, beat themselves up because, and I think a PhD programs sort of do this to you. Like many PhD programs like convince you that that the thing you need to do is sort of this singular individual accomplishment, like it's your project and your thing, and almost anything useful that you're going to do in the real world is like lots of people working on very complicated problems that are too big for one person to solve alone. And when you get into that mode, you get this new superpower of teams where you can have the person that's a better theoretician and a person who's better at the hardware and a person who loves to run experiments in the lab and a person who likes to write the code, and like you can build that complementarity inside of a team where you've got all of your bases covered and you don't have to be all of that in one person. And like I know a lot of people who waste a lot of time beating themselves up because they're not good at a thing, or they just naturally gravitate away from certain things and then just feel guilty about like not giving service to this other thing that they think is important, which is to me a horrendous waste of time.
Yeah. I mean, it comes back to, I think, the first part of this conversation around finding that thing you're passionate and going down that path. So yeah, I think that the other thing that I have seen in some of these programs, mine particularly also, is a push to do this singular new thing, not only on your own, but that is totally isolated and isn't built on the work of others or the vast knowledge of humanity we've been building up over these years. So then you're almost forced into something that isn't going to have, that applied value. I think that's something that, at Helion, when our fusion systems, we have looked at that they're built on physics and engineering that go back to the 50s. And it needed new electronics and new fiber optics and all kinds of new technology to be able to build the systems people had theorized, but it wasn't us starting from scratch. And I think that, the famous quote of standing on the shoulders of giants lets you move a lot faster and add real value to humanity quicker. And that's something maybe early in my career, like thinking about the space shuttle and those massive programs with, I don't know, thousands or tens of thousands of engineers and scientists that came together for those big projects to have a deliverable. And I think that I still think back to those sometimes. And when I talk about thinking about how I build teams at Helion.
Yeah, and some of these programs that we did in the space race in particular were just unfathomable in scale. Like there was a really good YouTube video from this YouTuber called Smarter. His channel is Smarter Every Day, and super good engineer who like makes great STEM content. And he was interviewing a NASA engineer who'd worked on the Saturn V program. And it's more than 100,000 people working on that program to like build this rocket that would be able to transport a moon lander like all the way to the moon and like get someone back safely. And it just crazy complexity of that thing, and like they're building it at a time where they have a tiny fraction of the scientific and engineering resources that we have right now. So I'm always in awe that like you could get 100,000 people, although like Microsoft's like bigger than that. It's always amazing to me that you can get people to large groups of people to do very complicated things. But I don't know, so impressive some of those past projects.
And I think about that in the scale of the project, but also the time. Like we went, if you think about where we went from, only tiny little rockets launched, essentially blowing up there wasn't even a pad yet, to lots of humans, massive scale infrastructure, and then humans like actually delivering that landing on the moon in that short time. And we've had lots of other projects too, where we move fast, where you start with this singular mission of I have a time limit and I better do this. I mean, you use the word race. That I think that's a big important key.
Yeah.
And I think that applies to fusion in some ways too, in that the time pressure on fusion is here. Like we need it. The world needs it. And so now you actually see people getting into this with that race mentality of how do we deliver this thing fast? And you then make engineering choices based off of speed, not always based off of the optimal engineering, but based off of what can deliver the mission, the product, deliverable as fast as possible.
Yeah, and so I want to get to fusion and Helion in just a minute, but I want to ask you one more question. So you had this amazing high school teacher who helped spark your interest in physics. Like, how did you go from like very interested high school student to, I'm guessing you majored in physics in undergrad, you got a PhD in physics. Like, what was that path? Like, how was your journey through college, and like, what was your first job as a physicist?
Yeah. So interestingly, in high school, I got the bug of, I want to go down this applied engineering and physics path, and I want to solve a big problem. Okay, that's not unusual for a high schooler. But I had now access to the resources to say, well, what does that mean? And so I looked at the time at the world and said, we need to solve energy. We need to get away from oil, not necessarily for climate change reasons at the time, but for all the geopolitics reasons.
And when was this?
So that would have been in high school in the 90s.
Okay.
In the 90s. And you look at in the universe, and the universe is fundamentally most of, if not all, the energy, it comes from fusion. And in some long, inefficient way, even oil comes from the plants that decayed, that were powered by fusion, and the energy came from there and was stored from fusion energy originally from the sun. And so you look to that and you say, great, we should be able to do that. Humankind can solve these huge problems. We can solve this one too. But tried to figure out how to get to that path. So then I got the bug of plasma physics and learning about the sun and astronomy and cosmology and stellar physics and plasmas, but in an applied way. And so even early, I was thinking about plasmas and plasma thrusters and fusion and all of those types of things, with the eventual goal of like, okay, I want to master this fusion thing, but I don't even know how to get into it. Interestingly, though, at the time, I actually couldn't afford college. And so to go to the schools that I knew were the ones that could do this. And so I actually spent 2 years at a smaller school in Texas, University of Texas, Dallas, a smaller school, learning electrical engineering, learning some of the core engineering and physics around this, with the goal of like, I knew what I wanted to get to, but I knew these were the steps. Spent 2 years there, and then spent 2 years finishing my bachelor's degree at the University of Michigan. And went off and started at that point was doing research in the plasma physics. This was in aerospace engineering with focus on the plasma physics or plasma thrusters, and then working in the nuclear engineering department on fusion, in fact, antimatter-based fusion. So we called that muon catalyzed fusion. And so my first technical paper was there as an undergrad in antimatter-based fusion.
Nice.
And then I kind of reached a crisis in my career where I looked at where I was looking at my career going, and I wrote this awesome paper and learned all this physics around fusion and saw the paths at the time, and looked at this and said, man, we're not going to materialize this in my lifetime. Maybe, like, when is the first electron on the grid coming from fusion? And it's not clear that even the machines I would work on would be able to deliver that before I retired, maybe even in my lifetime. And so I said, great, well, I've learned what I need to learn. Like, fusion's not ready for me yet. I'm going to pivot away from that, take my plasma physics and go build thrusters, go build spacecraft. So I went and worked, left after my bachelor's degree, worked for the Air Force Research Labs, building spacecraft thrusters. In fact, some of the thrusters I worked on were the predecessors to what's on Starlink now, those Hall effect thrusters. And some big high power things and some fusion related technologies as well. I went back to graduate school got master's degrees in nuclear engineering, more plasma physics, more aerospace engineering. And that's when I really got into fusion. I kept expanding that plasma physics knowledge. But it wasn't until later, after the PhD, after I was doing all this plasma physics work and the core around fusion, but applied towards thrusters, and some amount of maybe you could do fusion in space work too, that I met the core team at Helion, where I learned about some engineering ways that maybe can vastly speed up fusion. And that's where I got the bug and said, like, whoa, not only can we do space propulsion, that's great with this physics and engineering, but maybe we actually have a chance to do fusion on timescales that are relevant for humanity, relevant for me personally. Right? Frankly, it's relevant for me personally. And that's we were able to build those early machines, do fusion, and then I said, great, let's go do this. And we focus all of our efforts on forming Helion and moving from there.
So did your work on Hall effect thrusters, so for sure, one of the most important things about building a fusion reactor is being able to manipulate magnetic fields. And I'm guessing a Hall effect thruster is manipulating magnetic fields to generate thrust. So like how much of like this pathway of learning that you had, are your early projects influencing things that you're doing now?
Yeah, absolutely critical. In fact, a lot of the earliest work, I worked on Hall effect thrusters, but I also worked on very large scale pulsed plasma thrusters, where you're now taking a fuel, you're ionizing it into a high temperature plasma, you're superheating it up to 100,000 degrees or maybe even 1,000,000 degrees. But then you accelerate, you push it out of the thruster into space. And that's what gives you your Newton's laws, gives you your thrust. And then that pushes the spacecraft. And it can be very, very efficient. But here's the catch. In terms of efficient, in terms of mass, so you use a little bit of propellant to get a lot of acceleration out of it. But now it's all electrical. And so you have to be really careful that you're electrically doing things efficiently. You're ionizing efficiently. You're harnessing the magnetic fields and you're not wasting any. And so that's where that application of how can you do the most efficient engineering, because in a spacecraft, you don't have power. You're getting power from the sun. It's hard. Solar panels are heavy and expensive. So you have to save every single watt and joule of energy that's coming to that spacecraft. And applying that to fusion, turns out, is actually one of the ways to do fusion a lot faster, is if you can be efficient on all that. Hall effect thruster is the same. You have magnetic fields that are insulating and protecting the thruster itself from this very high temperature fuel. And the J cross B, the magnetic force, is what gives you the acceleration from that thruster.
Yeah. So I think that's actually a perfect segue. We've been dancing around this whole thing. You build fusion reactors. Like, explain to us how your reactor works.
Yep. Yeah, so our fusion generators, there's a couple of techniques of fusion, very high level. Magnetic fusion, which is a steady version of fusion, large superconductors, like a tokamak that holds on to fusion long enough that it superheats and then fusion can happen, it ignites, and then you use that heat to boil water and run a steam turbine. And then there's inertial fusion, where you do it this similar thing, but in a pulsed way, in a nanosecond. I think about it similar to a supernova, but in a nanosecond, you compress a fusion fuel. The leading way to do that is with lasers. Gets super high pressure where fusion happens. And then if you did your work right, it ignites, which means you get massive amounts of fusion power output, again, mostly in heat. Boil water, run steam turbines. What we do is something that takes some of those, the best of both, the physics of both, but then new engineering to do what we call direct energy recovery. So we take our fuel, trap it in a magnetic field that keeps it all protected, like in a Hall thruster or in a plasma thruster. And then rather than holding on to it forever until it ignites, we just squeeze it with magnetic field. Squeeze it as fast as we can. Fusion happens, pushes back on that magnetic field. And now I directly recover that electricity from that magnetic field back to recharge my systems. In the same way that for a thruster, I want to be as efficient as possible with every electron and every joule and every watt. I want to do that in fusion too. Key is, what we found is if you can be really efficient on the engineering and do really good engineering, you get to do less physics. The fusion physics is the hard part. And I want to minimize that so that I can build fusion systems smaller, cheaper, and all of those things.
Yep. And so, like by contrast, like the way that we've generated nuclear power for a while now for like powering um, yeah, the electric power grid has been fission reactors, where you basically put fissile material together, like they get very hot, and then you generate steam that turns turbines correctly or correct.
Yep, exactly. Exactly. You get the hot rocks that boil water, and they're very, very good at releasing heat, which is both the positive and the challenge. And then and use that to boil water like we know how to do, and then power the grid. And I think about it almost as the way we do fusion is like jumping over the combustion engine and going right to the electric car, where you very are efficient in terms of electricity through that whole process, so you can get more of whatever you need. And for us, that's electricity out.
So I want to talk like more about the engineering and technology, but I guess, an interesting question for everyone is like, why start a fusion power company? Like, we've been trying to build fusion reactors since when? The 1960s, maybe earlier. And we have. Yeah, I think there's this sort of joke that physicists make where, like fusion's always been 30 years away. Like every year you want to ask when it's coming.
Yep.
And so like we just haven't made a ton of progress over many, many decades of doing this. And like most of the efforts that we've had, to your point, have been big things like the National Ignition Facility, or this thing that the tokamak that they're building in Europe right now. So like big, gigantic projects that have not yet yielded a commercially viable fusion reactor. Like, what gave you the confidence that you were going to be able to go build a company, raise the capital, and like build a thing that you were going to be able to make commercially viable?
Yeah, that comes to interestingly enough, I think that goes all the way back to high school, to that student in high school of, I have to build it to believe it, and I want to test a theory. And yeah, sure, I just read it in the textbook, but I'm going to go build that thing, and I'm going to get on the roller coaster, and I'm going to measure it. And so for us, we in the lab, and in that case, the lab was a small warehouse, had these theories. In fact, a lot of it you can trace back to the 1950s. First published paper of this magnetic compression and some of the recovery is in 1958. Really great work done. And but before the transistor was commercialized. And we're talking about pulsed electrical currents. Like, it's pretty wild what people were able to demonstrate even then. And in those systems, those small systems, and these were funded by the federal government. So I'm all supportive of all the research money we can put into fusion, because we wouldn't be here without it. Small research projects, but literally in a small system that was 10 feet long, and I helped build and like actually turned the wrenches to assemble the thing. We built a small system that did exactly this, made a plasma, superheated it up to thermonuclear fusion conditions. Fusion happened. We saw it push back the magnetic field. We measured fusion reactions. We measured fusion particles. We measured a lot of it. And we did that on the program that was like $1.5 million, but was outperforming certainly every private fusion company that had come before. But then most of the national labs, even up to the $1 billion scale lab. And we said, like, wow, okay, we're seeing an approach that like can do fusion at scale, that fusion at a really interesting scale, still not at commercial scale, but for 3 orders of magnitude less money. Maybe, and this is something I learned at the Air Force working on those spacecraft programs, is that if the research, you can directly tie the final cost of whatever the deliverable is to what the research cost is. And that it only goes up as you start to build more complex systems and make them reliable and then make them deliverable, the cost continues to go up. So if you can do the research at $1 million, you can now deliver fusion systems at competitive rates. Or if you're doing the research at $1 billion, the commercial system is in trouble already. Yeah. And so I said, great, but that's not scale yet. We got to go figure out how to scale this. We haven't proven the engineering or the business case. We got to go figure those things out too. So we spent a couple more years doing the financial modeling and the scaling modeling of like, what does a generator look like? What does a power plant look like with this approach? Assuming everything still works as we scale. And both been demonstrated thermonuclear fusion, measured fusion reactions, scientifically validated and peer reviewed, and all of those things, plus a real clear commercial path if we could hit our milestones on the way, enable us to go and spin off Helion, raise venture capital. And luckily enough, we found some really good venture capitalists, Methril Capital and then Y Combinator, to help grow that technology, that we're a good believer in what we were doing. And then started hitting milestones. And then it took 3 more machines for us to build now the full scale fusion system, like we did and published about 1.5 years ago, our Trenta system that then got to full fusion conditions over 100 million degrees at fusions at commercial scale.
Yeah, one of the things that really impressed me the first time I saw that machine is just the number of engineering challenges that you had to solve. I mean, like, it's a complex machine. And so, to your point earlier, it's not just about a bunch of partial differential equations, and like, I'm sure the computer simulation piece of this is also, very interesting in telling you, like, what do you build and how you characterize things and whatnot. But just the sheer scope of, like, the little nitty gritty engineering problems and like the thing that impressed me about you all is, like, you just sort of took nothing for granted. Like, every piece of the system, like, has to be reflected upon and designed appropriately, and efficiencies wrung out of and whatnot. And, sometimes you can do amazing things by just making sure that you do every last piece of it meticulously. Like, how do you all approach that? Because it, like, strikes me as this huge multidisciplinary thing that you've got to go do.
Yeah, it is a good question, and I think that's one thing maybe that sets Helion apart, but it's one thing, at least at the very least, as we focus on from the beginning, is our approach to fusion directly and efficiently recovers all the electricity you put into it, so you have to do less fusion, okay? But that means you have to very efficiently recover all that electricity everywhere. So that you can minimize the fusion scale, the magnetic field, the coil sizes, all of those things. And so from the beginning, we've always been intentionally meticulous about every one of how the connectors are done, testing those connectors, making sure those connectors always work, and what's the limit of those. We do a lot of destructive testing to find limits. And so that has been really important and baked into the company. And I think part of that comes from that coupling early of people that also worked in the space field, where it's similar. You're building a rocket, that engine has to lift everything that's on the rocket. And if there's one part of it, if the toilet seat on the rocket is really heavy, now the engine has to be bigger, which means you need more propellant to power that engine, which means you need bigger tanks, which are heavier. And you have this exponential increase in complexity and scale. And so by minimizing that, you can, shrink the scale, shrink the costs, shrink in theory, the complexity too. And then it turns out that bootstraps, which I didn't really appreciate early in my career, is that big giant machines are actually harder to make than smaller machines. Yep. And you say, like, okay, great. Yeah, it's 10 times bigger. It should be 10 times harder, but it's not. It's 100 times harder. It's massive amounts harder. And if you're capital, and as a business person now, where I've taken on all those business roles, if you have to raise capital from different sources, or worse, international sources, and like a lot of what we're doing in Fusion includes politics now, where there's politicians and other kinds of big things involved like that have long time scales and a complexity, that you get so big that it just slows down. It gets too hard and too complex. And by going smaller, testing the small rocket early, getting good at it, proving those small systems, and then learning to build the big systems, you just move faster. And the systems end up being more reliable. And I wouldn't have predicted that early in my career.
Yeah. And I think, funny enough, like that principle is true for most things. Like, everything that you just said is also true of building distributed systems and like any kind of complex software system, or even organizations. Like, big is only a thing you should do if it's absolutely necessary, because there's a cost for big. Usually it makes you slow and less focused and everything, more like harder to lift, like the rocket. So if small is good, if you can accomplish what you want to accomplish inside of the envelope of small. And so I think it's actually one of the genius things about what you all are doing. Like if you look at these, fission plants that we, are attempting to build, like they're just gigantic projects. They cost tens of billions of dollars to make one.
Yep.
And like they're at such a huge scale that, and I'm guessing part of like the reason they're at a huge scale is like you're trying to amortize you fall into sort of the reverse trap of what you just said. You convince yourself that this thing is going to be expensive. And so the only way you can really, recover the cost of things, like you got to build this giant thing that helps you amortize the development and construction costs. And yeah, I mean, but like what you all are doing are building these things that are going to be, much more compact, potentially, which is just genius, I think.
Thank you. Yeah, I think the way you said it is that you convince yourself of the outcome, and so you get into a trap early. You say, it doesn't matter what the control system or the cockpit weighs on my rocket. It's going to be a huge rocket anyway. So then you just bake that inefficiency into the system, where we try very hard not to. Even from from the point of view of some anecdotes of where a lot of our magnetic coils are modular. They're made all the same. And in fact, not only are they made all the same, but they're made up of subcomponents. And those subcomponents are all the same. So we may have 100 magnetic coils that have 4 pieces each, or 4 like main coil segments, but you end up making 400 of those segments. There's all kinds of manufacturing benefits for that. But then the one I didn't really appreciate is that we break those segments into pieces like a human can pick up. And so now you get a delivery and a human picks it up and moves it over to the table. And when you have a big coil, I saw and one of the manufacturers I was visiting earlier this year, they were really proud of this 300-ton magnet they had developed. There was one unit, it was 300 tons, and they developed the boat to move it around and the specialty crane to move it around and all those things. And I'm just thinking internally, like, this is slow. This is too slow. Like, you need to have this broken into little pieces. And every time we get to a decision point of, okay, great, I need a forklift to move this. It's like, whoa, are you sure we can't spend a little bit more engineering time and break this into a more modular piece? Sometimes you can't. Sometimes the physics demands that it just has to be this way. But
yeah, and, I think too, this is another interesting thing that you all do. Sometimes you're building like very bespoke things, and sometimes like you are like taking things that are useful for not just building fusion reactors. So like rather than having to go build a new smelting process and new metallurgy and like new whatever to build a 300-ton magnet, and you're going to make exactly one of these things ever. Like you are, building, you're using things where you can build lots of them, and like maybe other people can, benefit from them as well. So you've got economies of scale and like the components of your system, which is fantastic.
Yeah. And the way you make it, I think there was something I learned about rockets early in my career that just floored me, because as an engineer, I had never thought about it, which is the way solid rocket boosters on the space shuttle, but then now, the Falcon rockets, it's like, what sets the size? Oh, bigger rockets are better. They're more efficient. They're, on and on. But in fact, there's a train tunnel you have to move this rocket through. And if you can't move the rocket through the train tunnel, then rather than having a factory that builds rockets, you have to make a factory each time you want to build a rocket. And it just radically changes the business model, and it changes your ability to learn and be reliable and low cost. And so that we think about that, like, what's the biggest machine I'll ever make? It's not in power. It's scaled by, I have to fit one of these through a train tunnel. And that's the biggest one we'll ever make. And if we need more power, we'll put 2 of them. And that's the way we design these, and we think about it. And then you build a factory, and people don't have to move every time you want to build another generator. You don't have to break ground every time you want to build a new generator. You just build the factory that ships those on site.
Yeah. So I want to jump up a level and talk about why fusion. So I think one of the things that most people miss is, like, obviously you want fusion because it will give you a renewable source of energy. Like we clearly have a problem with like our consumption of energy is releasing way too much carbon into the atmosphere, and like that's highly problematic for a whole bunch of reasons. You still have the same geopolitical problems that you were you were talking about before. They haven't gone away.
Yeah.
But like, I think the thing that people really miss, and like you probably have a better perspective on this than I do, is that starting somewhere in the 1970s, like we just stopped using energy at the rate that we had been using it before. And like, it's actually a staggering thing to think about. Not just like what happens if we could take the energy that we're consuming right now and it's like more sustainable, but like what happens if like energy becomes sustainable and cheap and abundant enough where you could use 100 times more, 1,000 times more, or 10,000 times more of it than you're using right now? What's then possible? So like to talk a little bit about like why energy matters.
Yeah, I think about this a lot actually. From two perspectives. One is just recently we're starting to use more electricity. We're upticking for the first time in a long time, where in the 1970s and 80s we plateaued in a lot of ways in terms of our energy use. I think that's totally right. But recently, electric transportation, probably computation and AI kicks into that too. And looking at ways to solve climate change by spending electricity then goes in and starting to increase our demand for electricity. The other thing I tie to in this is standard of living directly ties with access to electricity, low cost electricity. So you look at different parts of the world and standard of living, and you can say like, okay, great, they have more electricity access, they have more standard of living, however you want to define that. But I asked the same question, what happens if we had 10 times? Does that mean our standard of living would be 10 times? What does that mean? Would we have access to clean water? Desalination is the classic. There's a trigger at the 1 to 2 cent per kilowatt hour, where if you can have electricity at that cost, then now you can desalinate water through electrolysis and other methods directly. Clean water is now cheaper than it was to actually like pull it out of a river and purify it. And so suddenly, you enable some of those things, which are clear. But I think through, if you had the computational access where you can have large scale servers at everybody's house. You got to get maybe the server price down, but now you can actually do really interesting things on the computation and the cooling around that.
I think one of the things that maybe people don't appreciate or think about clearly enough is maybe everything good that has ever happened in the history of humankind is humans discovering new sources of energy and being able to put that energy to work solving problems that benefit humans. And so in a sense, like you actually want to be able to consume more energy. You don't want the consumption of energy to be a bad thing, because nominally consuming more energy means you're doing more of those useful things for humanity. Like electrolysis. One of the things here in the state of California is like we have parts of the state where you have abundant water and you have parts of the state where you have no water. And like one of the reasons that California is habitable is we spend an enormous amount of energy pumping water from places where it's abundant to places where it's scarce.
Yeah.
And like I think you're going to have to do more of that in the future with climate change. You really do want a world where you have cheap, abundant energy, which is why I think the problem you're working on is, like, I think artificial intelligence is a pretty important problem. That's the thing I spend most of my time working on. But I think your problem is more important than my problem. And my problem is dependent on your problem.
Yeah, at some scale, our two problems work together. I don't know that we know, frankly, what happens if you have more energy. More low-cost electricity, particularly ones, it has to be low cost. That's really important. If it just costs a lot more and you have more of it, it doesn't actually help the situation where the essentially effective cost of burning wood to burning coal to fission power and then to renewables that are some of the renewables, when you have access to good sunlight, solar power can be really low cost. You have these these stage gates for humanity that you unlock, so I don't know that we know the answer to that, but I'm excited to find out. That's for sure.
Yeah, and we probably have two generations who've never experienced like what it looks like when humanity is expanding its consumption of power. So like you just don't even have the pattern matching anymore for what it could look like, where you can just sort of think it's like, all right, the availability of energy isn't the barrier for me attempting to go solve this problem. Like I can think about that as like solved, and then I can make something else be the tough thing. Anyway, it's like incredibly exciting to think that we're as close as 2028 to having viable, cheap fusion energy and like a path to like making that ubiquitous. Like it's just an incredible thing to contemplate.
And I think some of it is not just access to to electricity and energy and what it costs, but it's also maybe even more subtle energy density. Like, why could we build cars? Well, because we could get energy dense enough to put in a tank that you could burn it. Why could we build jets? Because you could get Jet A and like actually carry it around with you. Even electric cars, I point to the very first electric cars actually were before the combustion engine. In the 1800s, there were electric cars that had a 5-mile range, but they were huge and inefficient, and the batteries didn't work very well, or there wasn't the transistor to drive a modern motor. There wasn't electromagnets. All of that. Those things didn't develop to where they are now. And now you can have really high energy density lithium batteries compared to other batteries anyway, and that gives you the range. And you have regenerative recovery of electricity, which gives you more range. And suddenly it unlocks the 200-mile range or whatever that was the threshold we needed for the commercial electrification. Can you do the same thing with shipping? Can you do the same thing with aircraft? And so if you can get energy and energy density and electricity density even, then maybe you'll be able to unlock some of those things. I think one thing, we talk about desalination and fresh water, but there's some other cool things if you can go one more order of magnitude in cost, which is that dissolved in all seawater, all our molybdenum and rare earth metals and all the things that we like go to very hard as I say we, but humankind in general, go to a long length to try to dig out of the ground and purify or recycle even. Now you have lots more access to these things, and everybody has access to them. It just takes that amount of electricity to separate them out.
Yeah. And maybe it gets you better access to space, and maybe it like gets you back access to better material science. And like there's just so many interesting things that it potentially unlocks. So we're almost out of time here. So the last question I ask everyone, and it's sort of a weird question because almost everyone I chat with has such interesting day jobs, is outside of your work, what do you do for fun?
Yeah. Well, this time of year is one of my favorite times of year. And it's what I spend most of my time outside of work and of especially working with my son, who's 7 now, is Halloween. I love it. I love it. And we're now building animatronics, and we're working on lighting, and we're working on automation and some of the electrical and the structural. And then the reality of like, okay, we're going to build this thing, but it's fragile, and we're in Washington, so it rains and like shorts out. And so this is my favorite time of year. And we just get to engage of how does a smoke machine work? The physics of a smoke machine is fascinating.
Fascinating.
So that
you're atomizing glycerin, right?
That's right. You're not actually making smoke at all. You're atomizing glycerin, but it comes out warm. So then you have to run it through a cooling bed to keep it in a vapor form or a semi-vapor form, but cool, so it condenses and stays on the ground. It's really, really exciting. Physics and engineering tied into that.
Dude, I bet that's amazing for your kiddo. So like that is yet another example of a good applied engineering project where he may not even be realizing that he's getting excited about pretty hardcore applied engineering because it's all about Halloween. That's awesome.
Yeah. So that's fun this time of year. And then a lot of time we engage with the sports teams, local sports teams. So, my favorite is the Everett Aqua Sox, which is a local baseball team. And at this time of year, it's the Everett Silvertips, which is a local hockey team. And then I got to go to see the Kraken first, the Seattle Kraken, the National Hockey League team. So we get to engage with the community in that way. And then also it's great with the kid to go to all these things, especially the minor league games. They're almost in some ways more fun. Watch 2 innings and then go run around in the field for 2 innings and then 2 more innings sitting in the chair, those kinds of things.
That's awesome.
Yeah.
Well, thank you so much for taking time out of your busy schedule to chat with us today. And thank you for what you're doing. I think we all should be rooting for your success and everyone else who's working on these fusion programs. I think it's a extremely important thing that humans solve at some point. And I'm very hopeful and optimistic about your team's ability to help get us further along the path than we are now.
Awesome. Well, thank you very much, Kevin. It's been fun.
All right. What an amazingly fascinating conversation with David Kirtley. So one thing I wanted to kind of to talk back on a little bit, we were talking before your interview about some of the potential that we have if we're inventing kind of this new form of energy and what can come from that. But I wanted to touch on something that David was talking about, which is building on the shoulder of giants. And I think that anytime we come to a new technology and kind of a new invention, it is obviously many times, I think, coming from what has been built before, right? But I wanted to get your take on that and to hear you maybe talk a little bit more about how important it is for us to continue to building on the work that others have done and not just, thinking that we have to be working in silos.
Yeah, well, look, I think the objective reality is that it's nonsense that anybody is truly building anything from scratch. The whole of society is only possible because of this very principle that we just rely on people before us and even people around us solving problems in ways where we don't have to think about every detail and go all the way back to scratch for everything that we're doing. You can expect phones to work and things to run when you plug them into the wall, that electricity is available, and the number of assumptions and things that we take for granted is just there for us to use to run our daily lives and to build new things is really amazing. And I think it's an interesting thing about humans. I was saying this at some event, I believe, just the other day. We're incredibly capable, all of us, for going from being completely amazed and surprised about a new invention to taking it completely for granted 5 minutes later. But I think that it's important, being able to, from a respect and dignity standpoint, you don't want to be taking anything for granted, but that ability to just sort of assume that things work and then build on top of them is actually really important, because it's the only way that we get to more complex things. And then, the humility that I think we all need to have, though, is sort of acknowledging in the way that David did, that you're not inventing the whole world from scratch.
Right.
That you only get to do what you're doing because so many other people solved so many other hard problems before you even got the privilege of starting on the hard problem you're working on.
No, I think that's absolutely true. And kind of speaking of hard problems, I mean, you talked about how in your own life that was something you've been drawn towards, and obviously that's been something that David's been drawn towards too. What do you think is just kind of the potential of finally solving this hard problem of things like fusion power? And you're talking a little bit, as we were talking before the start of the interview, before the interview started, about what those implications could be, and you and David got into that a little bit. But I'd like to kind of hear more from you on what you think those implications are from solving these hard problems.
Well, look, I think there's sort of two parts of it. There's sort of the necessity part of it, and then there's the, sort of optimistic and hopeful, expansive part of it. So the necessary part of it is one way or the other, we have to get to sustainable, clean sources of energy, and we have to have them be inside of the economic threshold of our current sources of energy. If we don't have that, we don't have substitutes for the current consumption of energy that make economic sense for everybody, we're going to have a very, very challenging set of climate problems that are worse than the ones that we already have, which are not great.
Sure.
And so, I think, when you look at a thing like fusion, like you shouldn't be Pollyanna and just sort of pretend that it's going to happen on accident, because we've tried very hard and like not gotten all the way there for many, many decades. But like you also shouldn't be rooting against it, because if you don't have a solution like fusion to the sustainable clean energy problem, then we have a very challenging set of zero-sum problems in society that are I think people don't realize how challenging they will be in the limit. And so like that's the necessity part of it. But like once you get fusion and it's cheap and you can roll it out and everybody can have access to this cheap energy that isn't killing the planet.
Right.
I think it is going to be really, really amazing what we can do. David mentioned a few things like purifying or desalinating water with electrolysis. So, like one of the problems we have right now is like clean drinking water for everyone. And it's just, you can't use electrolysis to do desalination right now because it's too expensive. But if you have cheap energy, you absolutely can do it. And to his point, it gets cheap enough where it's easier to desalinate things and to pump the water out of the ground. And like that is a really profoundly amazing thing to think about. And it is one of what is invariably going to be thousands or tens of thousands of things that seem impossible right now, or that haven't even entered anyone's imagination, because you just are pre-constraining what you believe is possible based on the past 5 decades of like fairly plateaued energy consumption. And like the thing that I said to David is, I think really true. Like the reason that we get to live in the world that we live in today is because we have figured out how to take new sources of energy and translate them into, doing things that humans want and need. Everything from being able to live in hot environments with air conditioning to, like having drinking water in very arid places to, being able to move around the world relatively freely to, just being able to take for granted like all of the energy infrastructure. You've got all of these machines that do all of these things for you in your day-to-day life, and you just, don't even think about, how it is they work. So all of that's been plateaued for about 50 years now, like almost as long as I've been alive. And I think getting back to a world where we've, because energy's, cheap and clean, like we can start having imagination again about like what to do with energy intensity is like really going to be fascinating. So I'm with every fiber of my being, I am rooting for the success of David's effort and like all of the others like it. Like it's just going to be hopefully an amazing future that we will live to see.
I hope so. I'm with you. I'm right there with you. I'm very excited and hopeful as well. All right. Well, that's going to be all of our time we've got for today. A huge thanks to David Kirtley for joining us. And if you have anything that you would like to share, please send us an email anytime at behindthetech@microsoft.com. And you can follow Behind the Tech on your favorite podcast platform, or you can check out full video episodes on YouTube. Thanks for listening.
See you next time.